Hi everyone, thanks for joining us this evening. I would like to begin by acknowledging the traditional custodians of the land that we're currently on, the Wadawurrung clan of the Darug Nation, and pay my respects to Indigenous elders both past, present and future, and also extend those respects to any Indigenous people who might be joining us this evening. To begin with, I'm Gabriella Quattropani. I'm a master's student here at Macquarie University, and I'm also the administration assistant for the Association for Astronomy, which is a student-led organisation that puts together these shows for you guys today. Before we get in, I'd like to welcome you to the 4th episode of Macquarie Space Travels, Cosmic Nurseries and Graveyards. As you can see, we've got some good news. We're finally on campus in person, but we also have some bad news. The weather has not been kind to us this evening. It's quite cloudy, but don't you worry, we'll be able to show you heaps of images that we've taken previously on before this live stream to be able to show you guys some really cool stuff. So, in previous episodes, we've taken tours through the solar system, through the Milky Way and beyond, and you can watch these episodes after this episode, obviously, and there'll be links to these episodes in the description below. I'd also like to remind you to use our social media hashtag #MQSpaceTravels, follow us on all our social media, which you can see on the screen right now, and also ask plenty of questions in the comment section. And our MQ Space Travels team might forward those questions on to you so that we're able to answer them on stream. All right, so this evening we have a very special guest with us tonight, and that is Professor Orsola De Marco. So she is a professor here at Macquarie, and her research focus is on binary stars, which are double stars that orbit each other, and how they can affect each other throughout their lives. So she's also the director of the Astronomy, Astrophysics and Astrophotonics Research Centre here at Macquarie, as well as the Association for Astronomy, the AFA, and she also does teaching, and she's taught me quite a bit throughout my degree here at Macquarie too. So welcome, Orsola.
Thank you, Gabby, and it's such a pleasure to be interviewed by you, my student, and see how far you've gone from the days when you were an undergraduate. I'm so proud. And so thank you very much for having me tonight.
Thank you for being here, Orsola, and I'd like to start us off. Where are we going?
So, as Gabby said before, we have a new theme for you on this 4th episode. It's from Cosmic Nurseries to Cosmic Graveyards. And so basically we're going to tell you everything about the life of stars, from when they're born to when they die. And actually one of the great things about tonight is, so it happens that the life of stars are often displayed in the universe as images of nebulae. And nebulae, you'll hear this word a lot tonight, are basically extended objects. So they're not like a point of light, like a star, but actually they're quite large enough that even at the great distances that all sky objects are, you can still see them and find within them structure and color. It's going to be a lot of fun.
Yes, sounds awesome. So where are we off to first?
So the first image we're going to bring to you is an image of a planetary nebula called the Helix Nebula. Now, you will have heard me say Planetary Nebula. You may recall that in the last episode, Angel and Devika talked a lot about planets of our solar systems, exoplanets, all kinds of planets. Now, Planetary Nebula got nothing to do with planets, and we'll talk about that later. What they have something to do is the death of stars. But before we go to the image, we're going to show you something really cool, how to find things in the sky. To do so, we'll use Stellarium, which is a free software, and Gabby will tell you a little bit about it.
Yes, so as you guys know, if you've watched previous episodes, we use Stellarium quite a bit. It's a free software, as Orsola said, and we'll have a link to download it in the comment section below. And basically, we're able to use this to find objects in the sky, at what time they'll be up, and where they will be up in the sky as well. So it's a very handy tool for us astronomers.
Handy indeed. And in fact, not that long ago, instead of having this amazing thing where you just start, it tells you where you are, what the time is, and what's up above and where you can see it, I used to have to calculate this knowing a whole lot of things. And you, Gabby, will remember not long ago when I made you do the whole exercise on how to find things with the calculator and yeah.
Yes, and it took quite a while. And I said to you, Orsa, I've had enough of this. There's better ways to do this, surely. So we ended up using Stellarium after all. So yes, it's very handy.
So I think Hannah now is going from the Stellarium image to our own image. If we had been in a clear night tonight, we would have seen that live as we were taking it, but instead we're showing you one that was taken a little early on. So what you can see on the screen right now is the Helix Nebula. As I said, this represents the death of a star, a little bit like our sun, maybe a little bit more massive than our sun. The nebula you see is gas ejected by a star during the last phases of its life. You will see in the geometric center of the image a very faint star. That is the star that ejected all the gas. Today, it is a white dwarf, like a pretty hot but very small star. In fact, as small as Earth. Like that's really small as stars go. And the gas around it is colorful. It's colorful because we color code different, either sometimes we color code different temperatures, sometimes we color code different elements. And you can also see a lot of structure in this image. The structure is got, you say, why is it a helix? Well, it's because if you could see this image in 3 dimensions, which we're about to do in a moment, you will see that actually it has a helical structure. The structure in a planetary nebula is due to something we don't fully understand. Now, as you can see in the movie that's about to play here, so this is the picture as you've seen it just earlier. And when you take images, of course, of the night sky, things are rather flat. But in fact, we of course know these are not flat things, they are 3-dimensional. Now, how could we figure out what the 3-dimensional structure of the object is? Well, there are many ways of taking images of planetary nebula and in fact all sky objects. Sometimes we just take photographs, sometimes we take a spectrum. A spectrum can tell you all kinds of things. It can tell you about the chemistry of the object, the elements that are in them, but also the velocities of each part of the nebula. And by doing that, you can reconstruct the 3-dimensional structure in a model. So what you're seeing here is not an image, obviously, but it is a reconstruction based on lots and lots of data. And as you can see, the nebula is very 3-dimensional. It has a bit of a bubble in the middle, and it has a little bit of a skirt around it, which in fact has 2 arms, a little bit like spiral arms of a galaxy. Now, a question is, what creates this incredible structure? After all, a star is spherical. Why doesn't it eject a nice bubbly spherical nebula? Well, sometimes they do, but most times they seem to eject these really complex structures. And the question is why? And it has something to do with binary stars, which is what I actually study. One other really cool thing before we move on to other objects is that this nebula is the closest planetary nebula to Earth, only 700 light years away. I know it sounds like really far, but we'll see soon what far actually looks like. And it's really large. It's about half the size of the moon. Now, you'd say, well, it's half of the size of the moon. It means you can see it. Well, I mean, after all, the moon is very obvious, right, in the sky. Mm-hmm. But the problem with planetary nebulae is they're super, super, super faint. And we'll talk a little bit about later about how we make faint images appear so bright in our pictures. And so they're very faint, even if they're large, because the gas within them is super, super rarefied, very low density. Mm-hmm. In fact, I have a lovely analogy. If you take a glass of water, well, if you take a glass and you put your hand on it and you trap some air in it, and then you take that air and expand it to the size of Mount Everest, that's how undense the nebula is. That's how rarefied it is.
Yeah, so planetary nebulas are obviously, these are the depths of stars, but why are we calling them planetary nebulas if they've got nothing to do with planets?
Right. So the name is historical. Mm-hmm. It goes back to William Herschel, who was really excited in the late 1700s forever and discovered Uranus. And through the rudimentary telescopes that they had back then, he had seen this nebula. He knew that they were not planets. It wasn't a mistake. But they look kind of roundy and cute and planet-like, so we call them Planetary Nebula. And the name has stuck. I don't know why people have not sort of moved on from it, but hey, we still have it today.
Well, there's a question in there for you, is what would you call them if you could rename them?
Right, so guys, maybe you can figure out a good name for this nebula, and if you do, please send it along, because astronomers are really creative with their names. We have things called the Big Bang, and we have things called the Milky Way, so we really love fancy, crazy names, right? So send on your suggestions. I don't know what I would call them. We kind of Dead Star Nebula. That's not very creative, is it? It's a bit boring.
It's got a bit of a Star Wars reference
Yes.
that most people might like in there. So we just have a question from the audience. So you mentioned there's a white dwarf inside the Planetary Nebula. So what happens to that white dwarf?
So white dwarfs are, I don't know if it's fair to call them dead stars. They're still fusing elements a little bit on their surface. So they're not quite dead. But over time they will. They'll stop, they'll run out of all fusible fuel, and they'll basically be cinders cooling off. It'll take a very long time, and they'll stay there and get cooler and fainter over cosmic times. Not very interesting.
Yeah, so and they'd be very hard to see after that.
Eventually they'll be very hard to see, also because as they cool off, their light will dim naturally.
Yeah. And we've also got another question. What happens to all this matter that's ejected from the Planetary Nebula?
So the matter is ejected at velocities of about 10, 20 kilometers per second. And that sounds fast, but in astro it's not that fast. And so it's literally coasting. It's not ejected in a big explosion. It's just out. And it'll coast out. And while it's still close to the star, it is very bright because the white dwarf in the middle is very hot. And that hot radiation ionizes the material around. That means it strips the electrons off the protons. And there's a lot of processes that can make light in that type of gas. However, over time, the thing will just get bigger and bigger and more rarefied until it just literally fades out. So most planetary nebula are approximately 10,000, 20,000 years old. And remember, that's kind of really recent. Like the last ice age was 10,000 years ago. And there's a few that somehow have remained still bright and they're 50,000 years old, but eventually they really fizzle away, just like the white dwarf.
Yeah, and they sort of, when they're puffing off their gas, they're sort of fizzling out. So they just keep fizzling out.
They keep fizzling out. And in fact, as our telescopes get bigger and we can take deeper and deeper image, deeper means just like how we just stack them up. We'll talk a little bit later about how we do that. We can actually sometimes find extremely faint and very large planetary nebulae. They're really the last bit you can see. And wait another 10,000 years and you will not be able to see anything.
Well, it sounds very interesting, but we're going to move on to our next object, which really fits into our theme of cosmic nurseries and graveyards because it's the Skull Nebula.
That's right. And of course, you already realized that while we were not very creative with talking about planetary nebula as planets, we are very creative in giving names and nicknames to our objects depending on their appearance. Now, the Skull Nebula is so called because the structure, just like the Helix Nebula had a lot of structure, the Skull Nebula has structure, and it has this kind of darker areas that could look like eye sockets in a skull. So the Skull Nebula is another planetary nebula. It is a lot farther away, and it is also a little bit smaller. And as you can see, it's really faint. It's a lot fainter than the Helix. It's also got a funny colory. So this image was taken by our telescope, and it was taken only in one band. That means with basically looking at the visible light. And it is interesting because you can see the color is kind of greenish. Mm-hmm. And this is what planetary nebula look like if you could look at them with your eye without taking images with different lights and then combining them with different colors. And the cool thing about this nebula is that it doesn't have one star in the middle, but it has three. It's a triple system, actually giving some grounds to the idea that the complex structures of this nebula comes from interactions of multiple stars in the middle. And the other cool thing I love about this, and actually I did my PhDs in this type of objects, it's that the star in the middle has no hydrogen. Now, you would say, and so what? Well, the universe is 9 particles out of 10 hydrogen. So a star with no hydrogen makes no sense. And at the beginning, people really said it must be a mistake. There must be hydrogen in there. We just can't see it. But there definitely is a way to strip stars of all of their hydrogen. And soon we'll see some structures that I can explain with regards to that. But before
we do that, so we've actually got one of our AFA members, Andrew, here, and he actually took this image of the Skull Nebula. And as we said before, it's really, really faint. It's really hard to take an image of, but Andrew's going to explain how we take images of these faint objects. So on to you, Andrew.
Thanks, Gabby. So I would have liked to have shown how to take an image tonight, but unfortunately, because it's cloudy, all I can do is explain how this image was taken. It was taken with our 9¼ inch Schmidt-Cassegrain telescope, which is a reflector telescope composed of 2 mirrors, and it was taken using a series of photos, each of 60 seconds exposure, and then stacked on top of each other to reduce the amount of noise and to bring out the amount of detail. As Orsola said, this nebula is considerably, it's about 3 times further than the Helix Nebula is, so there's a lot less light to be captured, and thus it requires an hour of data in order to be able to see it clearly.
Well, thanks, Andrew, for that. It's very nice to hear about what you would actually be doing if we were doing this live as well, but unfortunately the clouds aren't agreeing with us tonight. But anyways, so we're going to move on to the high resolution image now of this object, and you'll be able to explain a few more features from this image.
Oh yes, there's so much on this. I really love this object. I spent most of my career studying them and studying the stars in the middle. They're incredible. So this image is taken actually by a space telescope, the Spitzer space telescope, which is an infrared telescope. Infrared is not the same light that our eyes see. It's more the light of warm things. So it's a longer wavelength, less energetic light. And it is light that is typically emitted by warm dust. So what we're actually seeing in this image, you recognize the contour of the skull, but in the middle there is what appears, I call it a ring. It's hard to see it as a ring, but it's kind of a bit of a messy ring, right? And you see it's red. So what the people who made the image here did, they color-coded the infrared light to be red and the light from the gas to be green, so that we see the 2 components of the nebula. Now, the dusty ring is actually ejected likely by a thermal pulse when the initial nebula was already out. So it's like this nebula, instead of being ejected by a star that becomes the white dwarf as a poof, there are 2 poofs. The first one is the one that makes the gaseous greeny outer part, and then a later poof is made this inner part. Now, it might be hydrogen deficient again, like the star doesn't have any hydrogen, and it's like the last of the star before it's really gone. Now, what I love about this image is that it's got 2 colors. The other one was a little bit boring, was just green. And we should really point something out that is quite important. So in astronomy, often we make these beautiful pictures that have a lot of colors. If you were able to fly to the object and see it with your own eyes, you likely wouldn't see all those colors. You just see something that maybe is a little bit greeny, right? Like the other image we took. And I remember once, back when I was in New York City, that the New York Times published a beautiful astronomy image, the colors just like this one, and said, well, this image might be beautiful, but it's fake. And I got really mad because I said, it's not fake. It's not what you would see with your eyes if you were in front of it. However, the colors are not fake. The colors come from, one is in infrared light, the other one is optical light. We combine them with different colors to show that the dusty part that emits infrared is only concentrated in the ring. So it's a representation of very much reality. And so I think, images in the end tell a million stories because you can do things as clever as we do with astronomical images.
Yeah, and what's interesting is that this nebula has those 3 stars instead of the singular star. So are these interactions between all the 3 stars actually affecting the nebula itself?
So yes, absolutely. And actually in my about 10 years ago, I was so amazed about the multiple shapes of planetary nebulae. And I was so even more amazed by the fact that most astronomers thought that binary and trinary stars, so these are like multiple stars, didn't really play a big role in making these incredible shapes. And I was thinking, how can it be? And there were some astronomers even back then that said, well, it has to be with this interaction between stars, why they have these incredible shapes. So I took it upon myself to really try and dig deep about this topic of the relationship between dancing multiple stars and the crazy ejecta and nebula that they made, and worked really hard on it. And today we're reasonably sure we can start understanding the shapes as a result of the stellar interactions. Now, as you said, the stars interact, and that's because there's two stars, remember, they're not solid objects, right? They're made of gas. And so when they're close enough, their mutual gravity can pull matter off each other. And this matter does all kinds of things. It streams from one to the other, then it gets ejected in winds. And you can imagine, the things are swirling and swirling. It's like being in a food blender, right? And so you see this nebula end up having this shape. Sometimes they're spiral arms that look like galaxies. And yeah, so it's definitely a big influence of these interactions.
So does that mean when we were talking about the white dwarf sort of fading away and we might not be able to see it anymore, could we perhaps infer whether or not there's another star there from the shape of the nebula, if it's sort of a weird shape?
That's a really good word you use there, inferring, because so one of the difficulty with proving that these beautiful shapes come from these interactions is that sometimes you don't see the two or the three stars. In this case, you do. But many, many times you have crazy shapes and in the middle you see one star. So what does that mean? Does it mean that it's one star, or does it mean that the companion is just too faint? So we're reasonably sure that it's the latter, that it is that the companion sometimes, the white dwarf is quite hot and obvious. The companion sometimes is like the sun or even less massive than the sun. So at those distances, you just can't see them. They're too faint. And they're also very close, because the stars interacted, they're actually very close to one another. And, once you move them to the distances of 1,200 light years of these objects, then you suddenly don't see them as two different points of light. So you have to infer it from the nebula rather than directly detecting it.
Yeah, so we've had a question about the different colors in the image, and one from Jimmy Bainbridge was asking in our telescope of Macquarie Observatory if any other filters were used because it's so faint.
So so this one that we talked about was from the Spitzer Space Telescope. The previous one was ours, but in that case we didn't use different filters. The previous one, the Helix that we did, would have been, often what you do is you take images in 3 filters. And for Planetary Nebulae particularly, the way you do it is you center the filter on particular wavelength where the nebula emits a lot of light. And Planetary Nebula, the one wavelength where most of the light come out, is in a oxygen, doubly ionized oxygen. So that's oxygen that's lost 2 electrons. And it's at one specific wavelength of 5,007 angstrom, or 500.7 nanometers, for those of you who like wavelengths. And it comes out in that. And so you would center one filter on that. Then you might do one on the light of hydrogen, and then you might do one in the light of sodium or nitrogen. And then you say each of these images will color code in a specific light, maybe blue, red, and green. And then the combination of the 3 can give you not only the beautiful color, but the information of where these ions are shining from. So often the oxygen is inside, whereas the hydrogen is everywhere. So you get these localized colors that are so beautiful.
Yeah. And it's also important to note that with filters, you're blocking out some of the light as well. So for faint objects,
correct,
you can make it even harder for yourself to be able to see anything if you're using a filter.
That's generally really true. But in Planetary Nebulae, it so happens that most of the light comes out in this oxygen wavelength and in the hydrogen wavelength. So if you had 2 filters just catching that light, it would be most of the light of the nebula anyway.
Oh, yeah, very interesting to know.
In stars would be different because
Yeah.
they emit in pretty much in many, many wavelengths. And so the filter would just limit what you get, and you get even fainter. But with planetary nebulae, we're lucky in that respect.
Yeah, when we're talking about planets themselves, doing different filters, you can really cut out a lot of the light. And that's also because it's just the reflection from our sun as
Right.
well. So that's exactly the reason. And we saw that in our last episode as well. So that's really good. So now we're going to move on to the next stage in our stellar life cycle, I guess. And do you want to introduce our next object?
Yes, so we're moving from graveyards and a little bit back in time to an earlier time in the life of stars. And our guests might wonder why we're going backwards. And the reason is that we hope we would be able to open our telescopes tonight. And of course, in astronomy, you're not free to look at whatever you want, whenever you want. You gotta wait for things to be up above you so that you can look at them. And so it happened that the objects we wanted to look at were in reverse order, right? So we kept our order hoping that we could be open tonight, but alas. Anyway, so we're going to not quite stellar nurseries, but rather clusters of stars. This particular cluster that you're seeing is called the Pleiades, and it's a group of stars. It's not particularly young. It's kind of, imagine a family where the kids are teenagers or young adults, okay? Now, why do I call a cluster a family? Well, because stars are born in groups, which we call clusters. They're pretty close to one another. And while they're still young, they're also still grouped, and you see them as clusters. And the Pleiades is particularly cool because we can see them with the naked eyes. And it's a grouping of 7 stars that we can immediately pick. They are quite close to one another, but if you squint and avert your vision a little bit, you can see them. They're called the 7 Sisters. From, of course, almost everything on the sky has got some mythological reference to Greek mythology. The 7 sisters were the 7 daughters of Atlas and Pleione, and Atlas was one of the Titans, and the Titans were the gods before the gods of Olympus, and then the god of Olympus won the war. It's like a soap opera. Yeah. So anyway, going back to astronomy, yeah. So we got the 7 sisters. There's a lot more than just the 7 bright stars in the Pleiades. So the image you're seeing right now is our own observatory image, and there's a lot to say again, as always in astronomy. So you see that there's the bright stars, and then you got a little blue halo, right? In some of the stars it's more obvious than in others. So this cluster is about 100 million years old. And again, people say, oh wow, that's old. It's not that old in astronomical standards. Think about the sun is about 5 billion years old. So that's 100 million is a lot less, right? So, and they still have, there's quite a lot of dust around the stars. And this dust happens to have large grains, and large grains pick up photons and scatter them around in a way that the blue photons, so the bluer light is scattered in preference. And so that's why you see this blue haze around it. If you exposed the picture for longer, you might actually get more of this blue light as we're seeing. This is not our own image. The credit is right next to it. It's just a deeper image, and you can see how hazy they are, right? And yeah, so the haze is also sometimes provided by the fact there are lots of stars in there, some of which your eye just can't distinguish. So it contributes to the confusion of the image. But it's truly spectacular. Yeah,
so this cluster isn't just made of those 7 stars. It's made of lots and lots of stars, like hundreds of stars in this cluster. And the term for it is an open star cluster.
That's right. Actually, that's good that you bring that up. We got, so clusters are just usually the birthplaces of stars. But we have seen very, very diverse clusters. Some of them are very populous. You might have thousands or even tens of thousands of stars. Some are really, there's not that many. Some are really young, and we'll see one very soon where they're so young that it's the most massive stars are still living there. And then some of them are very different, like globular clusters. Now, globular clusters can have a lot more stars. They're very spherical, and we don't really, and they don't live in the galaxy. They live kind of around the galaxy, and it's really complicated and not clear to know exactly what exactly do they do, and they're old as well. But going back to open clusters, one of the interesting things about them is that as we said, are born all at the same time. And what's born in a cluster can be all kinds of stars, little guys and the supermassive guys. And the supermassive guys live very short lives. They literally live a blink of an eye compared to the little guys, the low mass stars. And in this, and so the highest mass stars in a cluster like the Pleiades have already long gone dead.
Yeah.
And only the intermediate mass stars are still there, and the lower mass stars.
Yeah. And what's cool about this star cluster, because they're all born together, they'd be all made out of the same stuff?
That's right. So stars are formed in incredibly large clouds of gas and dust. And that material has a chemical composition that is due to the fact, well, there's hydrogen always. And then whatever the previous generations of stars would have given out into the nebula, into Planetary Nebula, for example, and enriched that material. Now it's all mixed up together, and you're going to make new stars out of that. All these cluster stars are made of that, of the same material. So it's like you have a label on your shoulder saying, hey, I was made here at this time. Now, when they disperse, eventually over time, because they all have their own motion, they just literally drift away. And then at a later time, you might not be able to say that that star here and that star there belong to the same family. However, because you can study the chemistry of these stars, you can tell. And actually, this is a fantastic property that allows us to trace back the origin of these stars to the location and place and time where they were born. And it allows people to figure out how galaxies are assembled and how they evolve. In fact, this very property you identified is at the heart of a whole field in astrophysics called galactic archaeology, which is you tag chemically the stars, you figure out their life history, and then you understand how the galaxy they were born in are formed due to this property.
Well, I'm glad you mentioned galaxies because they're my favorite objects, and they sort of have to be because I'll be studying them next year for my master's. And galaxies are another example of a grouping of stars. Now, they're not a nebula, but ancient astronomers might have been a bit iffy as to whether or not they were.
That's right. So you could call a galaxy a cluster. It is a cluster, but they're very different. They form very differently, and they also have a lot more stars. So, you know, our own galaxy is 100 billion stars. I mean, that's a lot more than a cluster. Also, galaxies have specific shapes. We're about to see one of our own galaxies that we have taken a picture of from the observatory. It's called the Sculptor Galaxy. What you see here, it looks a bit like a cigar, but imagine it's actually a plate, right? A disk that's seen almost edge-on. So that's why it has this elongated shape. This is a spiral galaxy. They're flattened and they have kind of swirly structure, spiral arms in them. Not all galaxies are like that. Some are more like a cluster. They look like a blobby and oblong. And they have a lot of stars. And as you said, in the olden days, they could be seen with telescopes. They're actually quite large objects. But people thought they were nebulae in our own galaxy, just like other nebulae. And it wasn't until the 20s that people started realizing that they had their own special motion. And with that, they figured out where they were. And they figured out that they were really far and definitely outside of the sphere occupied by our own stars. And so that's when it was realized, oh my God, we are in one too, right? Of course, it's very hard to know that you are in a galaxy when you're in a galaxy because you don't see the galaxy, right? So, in fact, actually, I should point out that we call our own galaxy the Milky Way. And the reason we call it the Milky Way is because if you go to the dark side, so not Sydney, not Melbourne, not a big city, what you'll see at night is a band of brightness that will be somewhere in the sky. It's actually patchy because there's dust in the plane of the galaxy that blocks out some of the light, but it's definitely clear to see. And it's whitish because it's starlight, and so hence the name Milky Way. And what that is, it's actually the plane of our galaxy. When you're in that plane, you're just seeing from the inside. It's weird to think about it, but we're not our galaxy is not that dissimilar from Sculptor that we've just seen.
Yeah, I always like the analogy that you can't take a picture of your house when you're inside your house. basically.
Absolutely.
So that's all those images of the Milky Way that we see online, that's actually made from models or computer images. That's not actually our Milky Way.
That's right.
Yeah, it's very interesting. So when we're looking at this sort of image, you can sort of see there's stars in there, and we obviously know that that's a galaxy, it's not a nebula, but I can understand where the astronomers, if they didn't have as powerful telescopes, would get this idea from. And two galaxies that actually come to mind that people get confused with nebula a lot is the Large Magellanic Cloud and the Small Magellanic Cloud.
Yes, so these galaxies, we could just do a whole 3 hours just on one image because they're so interesting. So first of all, let me just tell you something. When I moved to Australia 12 years ago, I remember I was so excited about living in a place where you could see the Magellanic Clouds every day. And I remember asking my fellow Australians, oh guys, have you ever seen the Magellanic Clouds? And most of the people, grown-up people who lived here all their life, don't really know about them. And they are actually quite obvious.
So keep an eye on talk about features.
Okay, I think the audio's back.
Yeah. All right, so we had a few technical difficulties there. I think we're all back now, which is good.
Great.
We're not quite sure where we lost you, but we were just talking about the Large Magellanic Cloud being a cloud on the sky, and that it's very visible from a dark sky.
Yes, and I'm inviting everybody to really go outside, particularly if you don't live in Sydney, and take a look towards the south. And if you're looking at towards the South Pole, is on your right. Well, it'll depend on what time of the night, but it'll be towards the south. And as I was saying, the first time I saw the Magellanic Clouds, I was in South Africa, and I was so excited. It was my first trip to the Southern Hemisphere, and I took a map and I went outside, and I was absolutely ready to see them. And I looked up where they should be, and I saw there was clouds. And I thought, oh, really? And so I waited for these clouds to pass, and they didn't pass. And they didn't pass, of course, because I was looking at the Magellanic Clouds. So they really do look like clouds at night. They're enormous compared to what I would have expected. So when you can imagine, if you see them so big with the naked eye, you can imagine how amazing they look through a telescope. And we have an image from our own telescopes that we'll show you in a moment, where you will see, first of all, how ungalaxy-like this thing looks. It's, I don't know, I don't see anything. There is a little bit of a flat bit in the middle. Now, the reason they are so messy is because, I keep saying they, we're looking at a large Magellanic Cloud here. There is a littler one, also very messy, called the Small Magellanic Cloud. And these two galaxies and our own galaxy are kind of revolving around one another. And in so doing, they're stripping each other of stars as the mutual gravity just pulls the stars off. And that's part of the reason of why they're so fluffy and messy. Now, look at the image. This is an image taken with variable colors. And you can see there's some redness, and there's some whiteness, and there's some blobs and nebulae. And what is really cool is that in this galaxy, you can see the very nebulae that we were talking about earlier in our own galaxy. For example, you have a very, very bright blob. What is it, Gabby?
Well, I know what this is. It's the Tarantula Nebula right up there. And it's a very cool nebula. But before we get into that, I'd just like to remind everyone to send in your comments in the comment section below, because we can answer them on stream, and we'd very much like to do so as well. But to continue, this is the Tarantula Nebula.
Yes, so the brightest thing that you're looking at is the Tarantula Nebula. The Tarantula Nebula, we'll talk a little bit later about this type of object. It's basically a stellar nursery where it's a cluster, and it has lots of stars, but it's much, much younger than the one that we looked at before, the Pleiades. And it's actually an enormous stellar nursery. It's like a whole hospital full of babies, right? And in fact, there's nothing like the Tarantula in our own galaxy. But there's also other little bits and bobs of cloudiness and nebula there, all of which are, there are lots of star-forming regions. You could even see planetary nebulae in the Magellanic Clouds if you had a little bit more powerful of a telescope than we do. Now, what is interesting is the planetary nebulae can tell you a lot of things, aside from the lives of stars, which is what we discussed, but you can use them as little point of light that allow you to study how a galaxy rotates, because you can tell how fast they go and where they're going. So they're actually used as little probes of the kinematics, which means the structure of the galaxy and its motion. And they've been really used very successfully with the Large Magellanic Cloud and the Small Magellanic Cloud.
I think it's sometimes hard for us to recognize that the galaxies are constantly moving and rotating, but they're just doing so quite slowly for us. So we can't see it if we take different images of the galaxies over decades, but it is actually slowly moving around.
And that motion impacts them, as we said before, like their shape can change. And actually, I believe what you will be doing next year with Matt Owers, who studies environments of galaxies, is not just how the galaxy evolves and does its own business, but how being close to other galaxies influences it. And in fact, when we look at them, we think we're looking at the perfect galaxy, but they've had a lifetime of interaction. It's a little bit like stars. We were talking about binary stars interacting with one another, and indeed, that changes them. And that's the same, and the LMC is a poster child for having been bothered by something else in its life.
Yeah, it's really easy when we're just thinking about these things to think of them as something in isolation, but pretty much everything in astronomy, they're in clusters, they're in groups, and they're impacted by everything that's going on around them as well.
Absolutely.
Yeah, it's very interesting. But for the Tarantula Nebula, this you said it was like a stellar nursery. So can we have a look at another stellar nursery, maybe a closer one?
Yes, so to get the good picture of the Tarantula Nebula, you really need a lot of magnification, because it's a little object. You need to really just try to go closer, which we can do with a higher magnification telescope. But instead of looking at that one, we could look at a local picture of a local nursery. And in fact, it doesn't get much more local than what we're about to see. So this is the Orion Nebula. The Orion Nebula is also a stellar nursery. It is the closest stellar nursery to Earth. It's just over 1,000 light years away. And because of that, like a person that's close to you seems very big, and if it's far, it seems very small. Obviously, this has got, you can see it in its full glory. Within it, there is a cluster of stars. And because remember what we said before, that if you catch the cluster really early on, you're also catching the massive stars still alive. If you wait a little bit of time, the massive stars are the first ones to die and you don't see them anymore. So what we have here is a cluster of stars called the Trapezium. Well, the Trapezium Stars are the most massive of them, very hot, very massive. And what they do is when they're hot and massive like that, a lot of radiation comes off them, and it ionizes or strips the electrons of the protons for the gas around. And there's a lot of gas around here because it's very young, right? So it's like the afterbirth material still around. Oh, yeah. That's a bit of an icky analogy, but and so the material's all still there, the cluster's there, you can see the massive stars, and the colors is once again because we are selecting our specific wavelengths and we are depicting them in one specific color, which we're then combining to give us extra information compared to what you do if you looked at only visible wavelength, as we said before.
Yeah, I'm glad you mentioned that because this image took quite a while to make. And if those keen viewers might recognize it, that it's the one on my top as well. But what I'd like to do is go over to one of our AFA members, Chris, who can explain to us how this image was made and what sort of went into making a beautiful image like this one. So on to you, Chris.
Hey everyone, can everyone hear me? Awesome. All right, cool. So we're looking at the Orion Nebula. So this is, as Orsola said, it's a stellar nursery, and we've got ourselves one of the most beautiful, probably, nebulas closest to home. So this one you can actually see with the naked eye as well. So if you go outside when it's not cloudy, of course, you might be able to see in a nice dark area something very small right between Rigel and the three Orion's belt pretty much in the Orion Nebula. So if you have a nice camera as well, you might be able to take a long exposure shot of that, and you might get something quite nice. You might be able to see the Orion Nebula just on your own. Basically, so this image here is what we call a bicolor image. So this one was taken using two different filters. So we have ourselves what are called narrowband filters. So they're filters that pretty much what you want is one wavelength of color. So we don't want the whole red spectrum or red part of the spectrum, sorry, or green part of the spectrum. We just want particular wavelengths in each part of our visible spectrum. So H alpha corresponds to a very deep red color, and O3 or oxygen 3 corresponds to sort of a greenish kind of color. So this particular image was taken with the Tech 140 telescope. So it's a refractor telescope. So unlike the telescope that Andrew was talking about earlier, it is not a telescope that's made up of mirrors, but a telescope that is made up of lenses. So it's quite a different telescope, more of a wider field image as well that we get with this one. So this image was taken by Adam Joyce, who works up here at Macquarie University. And with this image, he has said to me that he's taken 15 minutes for each image, totaling at 4 hours per filter. So that's a total of, I'd say, 8 hours to take this image, which is quite stunning, I must say. But this took a lot of time to make and a lot of time to stack together. So what I said before was that you get each filter and you take, say, for example, 15 minutes, a 15-minute image, and what you do is you stack them using various programs such as AstroImage or so on and so forth, Deep Sky Stacker as well. And you can actually stack these images on top of each other and then take the O3 filter or corresponding H alpha filter and stack that on top of each other to actually make this image. So at the end of the day, what you can do is that when you get these images, you can make up whatever color you want. So it doesn't necessarily have to be green or red. You can say that I want to do this particular wavelength, I want to make it purple. or this particular wavelength, I want to make it orange. So at the end of the day, it's up to the photographer or the astronomer's discretion of what kind of color they want to make this image overall. But I would say at the end of the day, this is a quite a beautiful image that we've got here, and quite sad that it's not too great outside right now, so we won't be able to look at anything. But that's all from me, and back to you guys.
Thanks so much, Chris, for that explanation. That was really well done. So we've got a few questions that have come in actually about where Chris is in the dome. So where Chris is, she's currently sitting in front of our 24-inch plane wave, which is our newest and biggest telescope in the observatory right now. And a few keen people have pointed out, like, is that a plane wave mount? Yes, it is. It's our 24-inch plane wave. Yeah, it's our 24-inch plane wave mount, and it's quite our biggest telescope yet, and unfortunately we can't use it tonight because of the clouds, which is a bit unfortunate.
And I have a little story about it. So the plane wave arrived a year ago.
Yeah.
And we were keenly following as it came on the ship, and then it was through customs, and then it arrived and it was in the kitchen here at the observatory. And I am personally, I'm a theoretician. I work with computers. And we were here with Adam and Krishvab, who were looking at this thing, and I was saying, it's never gonna fit in the dome. It's never gonna fit through the dome slit. And they were saying, yes, it definitely will. Yeah. So a big crane came, and it was parked out in the grass, and he picked up the telescope, and the telescope was flying in the air. And I was very worried, but everybody seemed cool. And then they lowered it into the dome through the slit, which is the opening. And then in 3 seconds, everything was screwed on and everything was fine. It was very hairy, but very exciting. And now we have it, and it's working.
Yeah, and we've actually got a picture of it in the dome now that we've angled the webcam up a little bit more, and you can see how massive it is in that dome as well. And it's very. I'm so excited to have this amazing telescopes at the observatory. So our biggest telescope before this one was a 16-inch, and this is a 24-inch. So it's quite a lot bigger, and we can do a lot more science with it.
And in fact, we could say, so it's funny that we use inches, despite the fact that in Australia we use the metric system, but it's somehow stuck with astronomy. So it's a half a meter, and that is, you might wonder, what does that, is a length? Is that the length of the tube of the telescope? No, it's actually the size of the mirror. And the telescope itself is not a tube. It has actually, it's made of more like a scaffolding, right? And we're kind of seeing a little bit, the white part is the mount, and the telescope itself is just a lot harder to see the way our webcam is in the dome. Yes, but it is basically, I would call it the smallest telescope that is of research grade, right? Anything below that, even sometimes the optics are amazing, but would be definitely more like what you can buy in the shop. This one is really a fantastic tool, both for research, teaching, and for showing people the stars.
Yeah, and we're going a little bit off topic here, but this telescope, we're going to feed an optical fiber to it as well, which is very exciting.
So that is exciting because not only is the telescope extremely advanced, but we will feed the light from the telescope down the ground and into the laboratory that's next door to the dome. And in it, we have a spectrograph. And we talked about a little bit before how you split the light into its colors to analyze the chemistry in it. Well, we are going to do that with a spectrograph that was built here at Macquarie, and that is definitely top of the line, and we'll hopefully have students use it as well as the researchers.
Yeah, so if you're somebody who's in high school right now, I'd recommend coming to Macquarie to do your degree because you have access to all these beautiful telescopes as well. And we've also had a few comments talking about our little technical issue from earlier, and lots of people are saying it was aliens. It was not aliens, it was just our microphones playing up.
Yes, it was Orsola sitting on the mute button.
But that's okay. I would say if it was aliens, I would wonder why they're trying to stop us from talking about astronomy. Surely aliens would be wanting us to talk more about astronomy. But anyways, let's get back on to topic. So we looked at that beautiful picture of Orion that we've taken, and it's taken a very long time to take those images. But we've got a couple of images that we've taken these past couple of weeks from different telescopes at the observatory. So the one on the left is from the Celestron 9 1/4, and the one on the right is from the Explorer Scientific, the 102 millimeter. And you can see the differences in the images and how deep we can get with the different images and all these different exposures and how they affect the images themselves. And you can also see on the left, the core of the Orion Nebula is so overexposed. And that's because there's so much stuff happening there, isn't that right, Orsola?
Yeah, there's a lot of light. So we talked about with Christina and also Andrew before about the fact that to make an image that shows the details perhaps of the outskirts of the nebula, you really need to wait for a lot of photons to fall in your light bucket in your telescope. But of course, the downside of that is that you will overexpose the bits which are the brightest. Now, there is a technique to show the bright and the faint at the same time. You take one exposure that's not very deep. It means it's not very long, like you don't wait very long. And that will basically only show the bright bit. And then you take one that's really, really long and that shows the outskirts. And then you can combine them to try and make sure you don't have any overexposed parts like you can see here, which is, by the way, next to the Trapezium cluster where these very, very hot stars, very, very bright, are just, that part is just incredibly bright.
Yeah, so we're very lucky here at Macquarie Observatory to have all these different telescopes so we can take these different images and see how they're different through each of our different telescopes. And the bigger the light bucket, the more light we get, which is really interesting. So we're going to move on to a video, much like the Helix Nebula video that we had earlier, if you want to talk us through that.
So remember, again, the sky is like it's like going to the cinema. It's like flat, right? And so you'll only get two-dimensional images. However, when we take spectra and images in different colors, you can figure out a model of the three-dimensional structure of something. So here we're seeing a fly-through, the Orion Nebula, generated by a model. So this is clearly not us flying through. It is not real. But everything you see there is where it should be, and everything you see there has got the right brightness. The colors probably emphasize a little bit compared to what you might see with your eyes. One of the really cool things about Orion is these objects you're seeing right in front of you right now. So there are little stars, they're not particularly massive. Around them there are disks, and these disks are the disks where planets form. And then you see also these little jets that is like a byproduct of the disk formation. And the planets will be forming as we speak in these little disks. We call this object proplids. It stands for Protoplanetary Disks. And the material around it that makes a little bit of a cocoon is actually due to the Trapezium cluster stars ionizing and ablating and blasting effectively disk material from the disk and making these little cocoons. Now, the Orion Nebula has a lot of these proplids. In fact, they were discovered in the Orion Nebula, incredibly, famous when they were discovered. And I actually had a program with the Hubble Space Telescope a while ago to find more of these in other clusters, in other nurseries, but I didn't find any. And it turns out that this is not just, Orion's very special, not just because it's very close, but because it is at a very important juncture in its life where these planets are forming in this phase where you got the little baby planets. If we wait a little longer in Orion,
Can you talk?
Hi.
Yeah, we're back.
Okay,
Nice.
I think we're back now. So sorry guys for the audio difficulties and technical difficulties. Even some of our biggest telescopes have technical difficulties. The most recent example being the JWST Space Telescope.
Not to forget the Hubble Space Telescope that went up with the wrong manufactured lens, and it was basically short-sighted or long-sighted, and they had to go back up, send a space shuttle to fix it up and put some glasses on it. I'm not kidding, I'm joking, but it's definitely what happened. Anyway, all good.
All good.
So we had the question again. What was it?
So we had a question about what these jets are that are coming out of the disk.
So the material of the disk and of the jet and of the star is pretty much always the same stuff. It's hydrogen. Now, what happens when the disk forms is that actually it's not very hot. So when you have hydrogen gas, and of course, remember in star forming today, there's always a sprinkling of material from the previous generation of stars. So that could be some carbon, some oxygen, some calcium, and some all the stuff that makes dust. So what happens is these disks are quite extended and they cool. And when they cool, the dust condenses. And so what we have in this hydrogen disks is like bits of material, actually solids. And that's what you have in both the disk and the jets.
Awesome. So we've got another question from the audience, and it's from Jackie Hamilton, and she's asking, how do you account for movement within multiple images over such a long exposure?
Oh, okay. So first of all, well, there's two types of movement. There's astronomical movement that fortunately is not that much over the time of the image. And there is also movement of the telescope and movement of the kit, the machinery. And of course, the fact that the Earth is rotating, as is the sky. And so we need to have telescopes that are able to counter that. And
the telescope right there, you can.
Oh yes, look. So the telescope is, can you see it, guys? Yes. So the telescope is pointing at an object, but things are moving in front of it. So the telescope is able automatically to track the object as the Earth rotates. And of course, but there are other things. For example, think, I mean, there's lots of vibration. You know, we might not feel a vibration of somebody walking past, but it could be felt by the telescope pointing. So obviously you try to make sure, for example, an excellent point is that the telescope, in professional telescopes, the really big ones, they are stand on what's called a pier. So basically that's a bit of cement that's isolated from the rest of the building. So if people running around in the dome, it doesn't affect that vibration. So that's another method.
You shouldn't run around in the dark.
And one always does.
Adam's just telling us that we shouldn't be running around in the dome. He's our safety officer, so he has to put that out there. No running in the domes. We're just going to go back to our pretty Orion image, and we're just going to have a look at the different colors, because you've noticed here that those colors in the video, those were greens and blues, and these ones are reds and purple. So what's going on there?
Well, it's exactly what Christina said, right? So it's about a decision that you make to color things in a specific way. We already said that what you would see with your eyes would be kind of smudgy and green, right? Because our eyes are just, our eyes are tuned to the wavelengths emitted by the light of the sun reflected on the bits of Earth, the ground and the leaves. And so that's why we can differentiate so many beautiful colors of the rainbow in the visible range that we can see. But wavelengths of light are so many more, right? It goes all the way to the very short wavelength of, say, X-rays and gamma rays, and all the way to the long wavelength of infrared and radio. Now, we can't see all that, but our telescopes can. So when our telescopes detect light at a specific really long radio wavelength or really short gamma ray wavelength, we can color code that with whatever we feel like, orange, purple, whatever, and we can combine it. And then in the image, we'll say, look, what's red, it's radio emission. What's blue, it's X-ray emission. And we'll see soon another image where we do exactly that. So we get, it's like our telescopes are multiplying our senses of vision and allowing us to see so much more information.
Yeah, it's very important in astronomy that we do astronomy across all wavelengths.
Yeah.
We don't I don't know what I'm trying
We
to
don't
say.
select.
We're not very selective of the wavelengths.
Very tolerant.
We're very tolerant of all wavelengths, which is very good for us, and we make specific telescopes to be to use specific wavelengths as well. So we've got radio telescopes which look way different than optical telescopes, for example.
Yes, and of course we can't forget today that it's not just wavelengths, light, and electromagnetic radiation that we see, but we also see gravitational waves, right? So that's completely different, and yet is bringing yet another angle in information we can gather from the universe. And I mean, really, that's why we call astronomy today multi-messenger, because light is not the only messenger we have. We also have this ripples in space-time we call gravitational waves.
Yeah.
I mean, really, it's crazy, right?
Yes,
So-
yes. And we've just had a question about these dark patches in the images and whether or not they're dark matter. So are they dark matter?
So dark patches in images can be either just the absence of bright gas. Sometimes you can see, even in Orion, you can see some bits which are darker, even where there is a lot of brightness. That's usually dust, just dust in front, like, you know, like a cloud, a dusty cloud. And it's not dark matter, but dark matter is definitely there. But the reason it's not dark matter is because dark matter doesn't interact with light. So if you take a bit of dark matter and you put it in front of a light bulb, you're not going to see anything, right? That's what's so crazy and so difficult to detect, and we still don't fully understand what it's made of. We just know it's there because we perceive its influence through its gravity, right? So dark matter is definitely in great quantities everywhere, including in galaxies, because if it wasn't there, then things would rotate in a very, very different manner to what we observe.
Yeah, and it's also, we can use different wavelengths of light, like infrared, to study the dust, because dust is invisible to infrared as well, whereas dust will block out the optical light.
It's JWST.
Which
Yes,
as I mentioned, JWST is an infrared telescope.
That's right. And actually infrared is interesting because infrared itself is not just one wavelength, right? There's a whole range of wavelengths. So for example, if you go to the shorter infrared wavelength, then you will find that that dust is transparent, so you can actually catch material from behind. But if you go to the longer one, the dust actually is warm and it emits in those wavelengths. So you actually can reveal the dust, not just in silhouette in front of the bright light, but also you can see itself, which is a little bit what we did with the Spitzer image of the Planetary Nebula, the Skull Nebula, where we could actually see the dust in infrared.
Yeah, so just another example of why multi-wavelength
Yeah.
astronomy is so important as well, which is very good. So we're going to move on to our last object. We've got heaps of time left, so if people want to be asking questions, feel free to put it in the comments and we'll go back to some of your favorite objects if you'd like us to. But we've got to sort of end with a bang, Orsola. So we've done these little pulsars and we've got these stellar nurseries and jets coming out, but we want to end with a bang. So what's our last object?
What bang can we have if it's not the Big Bang? Okay, so we're not going to go to the Big Bang tonight. We are going to go to an explosion of a massive star. So we talked about stellar graveyards and we looked at planetary nebulae, which are the emission of gas from low mass stars. Now we're going to look at the nebula that is emitted or ejected by a massive star during its end phases. So we have here a little animation that just pans into the sky as if you could fly to the object, and you get eventually to the star of the show. And we're going to look at the Crab Nebula. So the Crab Nebula was ejected by a supernova explosion. Now supernovae, there are lots of different types, but this type is basically the explosion of a massive star, maybe 100 times the mass of the sun. Towards the end of its life, it's kind of burned anything it could burn. Remember, guys, that burning in stars is not real burning. It's not chemical burning. It's actually nuclear fusion. So you fuse various materials, hydrogen to helium, helium into carbon, oxygen, blah, 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 all the way to iron. Iron does not like to fuse and make energy. So what then happens is there isn't a way to make energy, so the star collapses down to as little as it can. Then some material literally bounces back out and creates this ejecta that you see here in this filamentary sort of nebulosity that you have in front of you. Now, what's left in the middle is a star, but it's not quite a star. We call them stars, but they're kind of really embers or cinders. If the star is very massive, it'll create a black hole. If it's a little bit less massive, it'll create a neutron star. Now, you can't, these are really, I mean, black hole you definitely can't see because it's a black hole. A neutron star is very, very faint. And you don't see it except through its interaction with the nebula that was just ejected. And so what we see in this nebula is usually a pulsar nebula. Now we'll talk about what a pulsar is in a second, but it's basically they're so small and so hot and they're rotating so fast that they heat the material around it, making a kind of a bit of a swirly nebula that we are about to see in the middle of the Crab Nebula. Now, I called them pulsars a moment ago. And so basically neutron stars, which are these tiny, dense, exotic objects, are they're about the size, they're much smaller than Earth. They're about 10 kilometers across or so. And they spin very rapidly and they have incredibly powerful magnetic fields. And this magnetic field is so powerful that they rip electrons and protons off the surface of the star. These get accelerated crazily around the magnetic field, and in so doing, they emit radiation. And the radiation is emitted in two beams, like two jets. Mm-hmm. Now, because they're spinning and because there's emission, you have like a lighthouse effect. Now, if the Earth is in the beam, then we see a bloop, 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 and we call these pulsars, and they come on a frequency which is the rotation frequency of the object, which in this case is 33 milliseconds. It's 33 thousandths of a second, tiny. And what we see right now, on the left, we have the visual object, the Crab Nebula, with inside its Pulsar Nebula. And on the right, we just separated the image of the Pulsar Nebula so to see it better. Now, remember we talked about having different wavelengths, combining them using different colors, right? So in here, the Pulsar Nebula is the blue thing. It's X-rays. So this is very energetic light coming from very hot gas heated by the crazy wind of the pulsar in the middle. And you can also see two little jets, right? And then it's overlapped to the optical image on the left image so that you can kind of see the size similarity or difference. Mm. And so you get a much more information this way by combining the colors. If you were in front of the Crab Nebula, you'd probably be dead because there'd be a lot of radiation. But aside from that, you wouldn't see these beautiful colors. You'd probably see another greenish subject.
Yeah, so these colors are again those representations of the different wavelengths that we're having a look at. And you mentioned that this was just one star exploding, one big star. But is there other ways to make these supernova explosions? Yes,
so first of all, I forgot to say something quite critical. The Big Bang that happened to make the Crab pulsar happened relatively recently. I mean, kind of recently. It was in 1054, and it was observed by Chinese astronomers who were excellent astronomers and very good recorders of the events. It was so bright that for weeks it was visible during the day. That's how bright it was. Yeah. And they recorded lots of things, including its brightness over time, which allows us today to analyze those data and figure out what it was. So as you said, there are lots of different types of supernova. This type is called a core collapse supernova for the reason I explained before. There's this a core collapse that makes the neutron star and then the bounce. But there are other types. For example, there are what we know as type 1a supernovae. The name is not particularly creative, but what these are actually the interaction, once again, interaction of two stars. And that's one star dumping material on a white dwarf. Remember the white dwarfs were the central stars of the Planetary Nebulae. So if you dump material onto a white dwarf and you grow its mass above a special mass, which is 1.4 solar masses, it's called the Chandrasekhar limit, then that star will no longer be able to be a white dwarf. It'll implode and try to make a neutron star. And that implosion and explosion gives you this other type of supernova. There's other theories about how you make type 1a supernova, like two white dwarfs smashing into one another. So of course in astronomy we don't know everything. Like we've learned a lot of things in the last 2,000 years, but we're still a little bit short. And so we that's another type. And there's a few other types around, but kind of the two main things are the death of massive stars and the coalescing of two white dwarfs.
Yeah, so it's very interesting how these stars can sort of interact with each other. And we've had a question about why it's called the Crab Nebula, and we had a question earlier about why we called the Tarantula Nebula the Tarantula Nebula. And do you want to have...
Yes, guys, here, as I said before, just, you know, knock yourselves out. You can really make up names in astronomy. So the crab, look, I don't see it, to be honest with you. You see a crab in there? It's very filamentary. Maybe, oh, you know why? And I was, oh, I see it now. Go figure. I'm far enough from my screen that I can see. So do you see those two reddish filaments kind of horizontally coming in? Yeah. It's like you're looking at the crab in the face, and he's got his little hands in front, right?
Yes,
my God, you know, I've been an astronomer for 25, 30 years, and I've never seen the crab. I'm excited now. Okay, so that's the crab. The tarantula actually has, if you see it from close, it's got all these legs, maybe more than 8 though.
Yeah.
Like,
yeah. So when we're naming objects in astronomy, we don't usually name them cool things anymore. They're usually numbers, because we have these big surveys in astronomy and we find loads of things all at the same time. So it's really hard to sort of stare at an image and go, what are we going to name that one? And we're sort of running around out of bugs and...
Yeah, particularly in the era of data science, where instead of 3 objects, you're going to do 3 million objects. You're not going to nickname all of them, right? But what is really cool is that there are actually, there's a body of the International Astronomical Union that regulates names, and sometimes there's little fights that break out about little names, and it makes me smile. But it's actually funny, because astronomers, as you say, right, we like, when you talked about the Tarantula Nebula that we were going to look at, immediately, I don't know what that is, but then you say 30 Doradus, and I know what that is, right? So we actually, in our profession, we end up really thinking about the boring name more often. And when you study stars for a long time, you end up actually knowing what we call the phone number, because sometimes the star has a very, like I still know the main star I studied during my PhD was called CPD minus 3072, right?
Have you ever rung the number?
Yes, I've never rang the number. I don't know what it is at the other end. But yes, so astronomers end up stuck with a boring name. So that's why I say, but you guys, you can really just go ahead and call them. We will take it up.
Yeah, so there's a whole union for naming all these things, and lots of debate around it, I'm sure. I guess it was much easier back in the old days when there was not that many astronomers around.
And not many objects.
Yeah, and you could just name it sort of whatever you want. And there's also the nice story about how Uranus was named, or Uranus, because lots of people find that naming funny. And originally the person who was going to name it, William Herschel, wanted to name it after King George. So that would have been even funnier if we had all these planet names. We had Jupiter, Saturn, and then George.
Yes,
I find that quite funny as well. So yes, astronomers do have sort of free range with naming these sort of things.
Yes.
But all right, so that was our last object for the night, but we've had a few questions about the galaxies, the Large Magellanic Cloud and the Small Magellanic Cloud, and how they interact and how we know that they've interacted. And I know that there's like a stellar stream, a stream of stars between the galaxies that we've identified. Do you want to tell us a bit more about that?
Yeah, so the Magellanic Stream is basically, I mean, if you took a picture, it'd be really difficult because it is incredibly faint. But what we do see is basically, if you have one galaxy on one side and one other galaxy on the other, in the space between, you see just a little spluttering of stars. So what are those stars doing? You know, they don't belong to our galaxy and they don't belong to the Magellanic Cloud. So who they belong to? Well, how do you even know? The way we get to know about the origin of those stars is that you figure out their velocity, so where they're going and how fast they're going. And you analyze each and every one of them and look at their combined velocity. And you realize that it's literally something that has gone a particular direction and is left behind a trail of stars. And then you can actually do much more sophisticated models where you look at the gravity of our galaxy, the gravity of the Magellanic Clouds, and you can even pretty much model individual stars in the two galaxies and smash them into one another. And did you know that if you take two galaxies that look very dense with lots and lots of stars and you pass one through the other, the stars don't collide, right? They are actually very far from one another, so much so that the chance of direct collision when two galaxies pass through one another is very small. But, of course, gravity is gravity, and so it will rip stars off in the sense that it will convince them to just be ejected from this one or the other system. And we do this not just with the Magellanic streams and the Magellanic Clouds, but it's constantly, in fact, Matt, your future supervisor, works a lot on how galaxies influence one another. And so this is a daily bread that stars in galaxies gets constantly perturbed. Sometimes a galaxy can be convinced to make new stars because of the interaction with another galaxy. So there's a lot of crosstalk.
Yes, definitely. And I think in one of our episodes, we did talk a little bit about galaxy mergers because we had an object where we were looking literally at an image of a galaxy merger as they were interacting as well, which was really interesting. Yeah, the Pavo cluster. So
that's right, and actually that is a fate of galactic groups where things will merge and get more blobby and.
Yeah, and also our closest galaxy, Andromeda, will eventually merge
with us, yes,
as well.
Exciting.
But not in our lifetime for sure, which is good for us, I guess. So we also had a question, we were talking about the supernova explosions, that we can't determine when something's going to be going off. We have to sort of pay attention to the stars that we think might be going off. And one example that comes to my mind is Betelgeuse. So do you want to talk a bit about Betelgeuse?
Yes, I don't know. Close your ears if you're afraid of big explosions. So Betelgeuse is a supergiant. So it's a massive star. It's definitely old for it. And we don't fully understand how massive stars explode. We can't say exactly what the characteristics of a star 15 minutes before explosion looks like. We do know that Betelgeuse is likely to explode. Is it next year, in 1,000 years, 10,000, maybe around multiple thousands of years? And what does it mean for us? You know, there's if it explodes in a particular way, very spherically, perhaps not as much as if it explodes with beam radiation. So that's actually one of the theories of stellar explosions, that they rotate very fast and they beam radiation into very narrow jets. If that were the case, and we happen to be in the right direction, then not so good. But yeah, so Betelgeuse, and there's other stars. There was a very famous one that was, so stars in massive stars towards the end of our life, some of them become very hydrogen deficient. We talked about stars with no hydrogen. And there's this one that is known to be close to going supernova. It was called the Death Star, nicknamed so by the press. It was an article came out in 2012, and you may recall in 2012 there was a movie called 2012 that talked about the end of the world. And the reason there was a movie called 2012 is because the Mayan calendar predicted the end of the world in 2012 with very good precision. Of course, the world didn't end in 2012, I should point out. And anyway, the Death Star was actually an article by an Australian astronomer, Peter Tuttle. And what was interesting about it is that it's actually a binary star and it has a swirly nebula around it. Now, the nebula is a perfect Archimedes spiral. And because of that, you can tell exactly the orientation. Now, the orientation was incredibly pole on, meaning you could see exactly flat. That means if it's going to beam anything, likely is towards us. So Peter talked about this in his article, and of course the press thought, oh, Death Star 2012, no. And that was that.
Oh gosh. Hopefully we don't have any Death Stars anytime soon. So we asked a question in the comment section about the Orion Nebula and what our audience would call it if they could name it, because the Orion Nebula is obviously named because it's in the sword of Orion. Yes. That's how it's named, not because of any shape. So we've got some answers from Andrew Kafala, who said the Flappy Bird. Do you like that name?
Yes, I do. It's got, but it's got two wings. One is small and one is big. Yeah, that's good.
You can sort of see it. Dear Cowdrey says the Cavern Nebula.
Okay.
Which I think we might actually have a Cavern Nebula. I'm not too sure.
Very nice.
And Mary says the Wondrous Nebula, which I think is very fitting. It's a very, very beautiful nebula, which is
I agree.
good.
I think it's nice, the idea of calling things according to the emotions they elicit.
Yes. And I get very happy looking at some of these nebula as well, especially if I'm taking an image and after my exposure finishes, then the plane flies through it.
Yes.
Because there have been times where we've been taking long exposures of images and we've had planes fly through our image just at the last second, which is very, very depressing and disappointing after waiting like 30 minutes for the image to come up and then it's ruined. So I'm very happy looking at nebulas.
But there's something that I don't know. I have been an astronomer for a long time, and sometimes you feel that the job is becoming a bit clinical, like you're looking at data and numbers. But when I look at some of the images that Adam and the students take here at the observatory, in fact, I asked Adam yesterday for some new images. I wanted to put them in a report. And some of them, there's just so many stars. And of course, when you look in a screen as well, you get the light effect and you can get lost in them. And I swear, like my heart races. It never gets old. And it reminds you how small we are and yet how amazing we are, how far we've gone with all our studies. It's just for once that you can be a little happy, right, in these difficult circumstances we all find ourselves in. So absolutely, just keep looking at astronomical images and remember, in the big scheme of things are okay.
Yeah, I think that's a wonderful note to end on, Orsola. So thank you for being our guest tonight,
Thank you very
Orsola.
much.
It was lovely to have you. I would also like to say thank you to the core MQ Space Travels team, which is Adam, Devika and Kelly as well. And also Ben for helping out with cameras and telescopes. And of course, the whole live stream could not be possible with our wonderful AFA members who are students here at Macquarie that are studying astronomy and are volunteering their time to help out here for the live stream. So I'd like to thank Andrew and Chris, who you guys saw on the stream, who were talking about the telescopes and would have been on the telescopes if the clouds were nice to us tonight. I'd also like to thank some behind the scenes people, which is Taylor, Mass and Kayla, who've been answering your questions in the comments and sending them through to us as well. And on a final note, I think, Adam, you can pull up our all sky camera to have a look at the weather right now and see what we're dealing with. So if people are wondering why we don't have the telescopes out.
Is that water?
This is water.
It's called rain.
It's raining here at Macquarie Observatory and there's loads of clouds, unfortunately, which is why we couldn't be live at the observatory tonight, but I hope everyone learned quite a few things. And I have some exciting news to share for everyone who has been wanting to actually come visit the observatory this past year. You will know that we've been closed because of lockdowns, but I'm very happy to share with you that next year in February that we'll be reopening the observatory. So be sure to follow all of our social media pages, which Adam will put up now. And yes, Adam will put them up now. Please, Adam.
Sorry, I was just reading the comment from Ursula's husband.
Oh, okay.
So we did a poll about the most favorite object.
Oh, okay. Well, we'll get to polls in a bit later, but I just wanted to finish this bit. So we'll be reopening the observatory, and you can find out more information about this in the new year when we'll post about it on all of our social media, especially our Facebook page, and you'll get information about tickets and how to buy them and how to actually come visit us and have a look through our telescopes, which is what we like to do. We like to have people come visit us, which is good. Now, I've been told I've got some poll questions and answers to have a look at, so
Question was, what's the favorite object?
What's the favorite object and who was the competitor? So out of Helix Nebula, Orion Nebula, the Pleiades Cluster and the Crab Nebula, 8 people preferred the Orion Nebula.
Very good.
I have to say I agree.
Yeah.
The Orion Nebula is the prettiest object out of all of them. And that image that we took probably the longest time out of all of them.
So it's good reward.
Yeah, it's a good reward that it's the prettiest object. It took the longest time to take, which is good. Sorry?
We have more episodes coming up.
Yes,
next year.
yes. Devik is telling me what to say. So next year we'll be this was our last episode for this year, but next year we'll be starting more of these episodes, and we hope to see you guys all at those future episodes. And remember, you can watch back this episode and previous episodes. They're all on our Facebook page, and for you to watch at your perusal. And yeah, I hope everyone learnt a lot, and from everyone here at Macquarie Space Travels, have a good night and a happy new year.
Bye.
Bye.